Welcome to Classification and Decision Theory. I am Dr. Jabbar Almaliki with the School of Computing at University Utara, Malaysia. In modern cybersecurity, professionals and automated systems are constantly forced to make split-second operational decisions based on incomplete, ambiguous, or rapidly shifting data. To manage this, we rely on decision theory, the formal mathematical study of making optimal choices under varying conditions of uncertainty. Every decision falls on this spectrum. Certainty means outcomes are entirely known, like blocking a blacklisted IP. Risk means outcomes aren't guaranteed, but historical data provides precise probabilities, like a 70% attack likelihood. Finally, uncertainty. Threats so novel that no probabilities exist. A zero-day attack is a prime example. Because the vulnerability has never been documented, analysts have zero historical data to rely on for probability mapping. Because these varying states exist, intelligent security systems cannot rely on human intuition. They require applied mathematical frameworks, specifically structural logic and probabilistic updating, to autonomously classify and neutralize incoming threats. Consider a high-stakes scenario where an entirely undocumented data anomaly breaches the outer perimeter of an enterprise network. This scenario overlay illustrates the immediate operational choice faced by the Security Operations Center. They must take action, block the anomaly, or monitor it. When probabilities sit at zero, decision theory provides three formal logical strategies to resolve this binary choice. The first is the maximum strategy. This logic dictates choosing the safest possible option to maximize the minimum gain. In cybersecurity, applying maximum usually translates to an immediate block. The priority is the absolute integrity of the system, even if a false positive interrupts legitimate user activity. Contrast this with the maximax strategy, which operates on the inverse logic, seeking the most rewarding possible outcome. An analyst might intentionally leave a honeypot open, choosing to monitor the unknown traffic. The high-risk gamble is that observing the anomaly will yield highly valuable threat intelligence. The third approach, minimax regret, mathematically weighs both options to select the path that minimizes the worst possible negative fallout from making the wrong choice. These strategies guide human logic, but modern enterprise networks move far too fast for manual deliberation. To scale defense, we must translate this logic into automated structural classification. To automate these choices, we rely on the decision tree. This is the foundational model used to codify human strategy into real-time computational logic. By reducing complex network behavior down into simple, hierarchical logic gates, a machine can execute decisions in fractions of a second. This diagram illustrates a decision tree building in real time. The starting point of the model is the root node, representing the initial evaluation of an incoming event. From that node, branches represent the logical outcomes of the evaluation, dictating the directional flow of the decision. When the flow encounters secondary decision nodes, the system is forced to query secondary threat intelligence to refine its classification. Finally, the branches terminate in leaves. These represent the absolute final classification of the data and trigger the resulting automated action. This structure provides two primary computational advantages. The rigid pathways are highly interpretable for human auditors investigating an event, and they are incredibly fast for machines to execute. This rapid, rules-based branching logic forms the backbone of real-time intrusion detection systems, where classification speed is the highest priority. But decision trees have a critical limitation: rigidity. If a threat mutates, the strict rules fail. A system's understanding of a cyber threat must be able to evolve dynamically as new evidence drips in. To solve this, we introduce Bayesian analysis, the mathematical engine for dynamic, probabilistic classification. The core premise of Bayesian theory is that it allows a system to mathematically update an existing baseline belief strictly based on the arrival of new, quantifiable data. This formula is Bayes' theorem. To understand how it classifies threats dynamically, we have to look at the individual variables. We begin with the prior probability. This is the system's baseline initial belief before any specific event occurs. For example, statistically, 10% of all incoming enterprise emails are phishing attempts. Next, we factor in the evidence, the introduction of a new, observable variable. In this case, an incoming email contains a suspicious, obfuscated hyperlink. The goal of the equation is to calculate the posterior probability. This will be the system's newly updated confidence that the specific email is malicious, given the exact evidence of the link. Let's walk through the calculation. Assume the total probability of seeing this link evidence across all emails is 0.25, and the probability of this evidence occurring alongside an actual attack is 0.17. By dividing the useful evidence by the total evidence, the math yields a precise updated probability of 0.68. The system's confidence in an attack just spiked from the 10% baseline to 68%. By crossing that mathematical threshold, an automated spam filter can now confidently quarantine the message without any human intervention. This split-screen visualization demonstrates both mathematical concepts running in parallel. Decision theory acts as the overarching strategic philosophy for handling uncertainty in a cyber environment. In application, decision trees execute the rapid, deterministic logic required to maintain outer perimeter intrusion detection systems. Bayesian analysis works alongside them, providing the dynamic risk prediction necessary for adaptive filters and continuously evolving threat intelligence. Within a security operations center, analysts rely on these invisible mathematical models operating in the background to transform chaotic, ambiguous events into quantifiable, actionable data. Mastering these specific classification techniques is essential for engineering the intelligent security architectures of the future. Thank you for attending today's lecture. Uncertainty is a constant in cybersecurity.